This is Anil Reddy, Assistant Professor of Mathematics, MLR Institute of Technology, Hyderabad. Today I am going to explain about Runge Kutta fourth order method. In this concept, we mainly concentrate on numerical solution of ordinary differential equations. So these methods, numerical methods, are used to solve the initial value problems for first order ordinary differential equations. So in the last class, we have seen Taylor's method and Euler's and modified Euler's method. Now we will see Runge Kutta fourth order method and how this method will work to help solving ordinary differential equation. Runge Kutta method are actually a family of methods. So these methods was developed by Professor C. Runge and it was extended by Professor W. Kutta. So after a few years later, so that we call it as Runge Kutta method. And the advantages of these methods are, and these methods have much greater accuracy than comparing to Euler's modified Euler's method and Picard's method. So it has much accuracy than these methods. And Runge Kutta fourth order method. So now we are going to see about Runge Kutta fourth order method. So in this method we have first order, second order, third and fourth order. So I am going to explain about Runge Kutta fourth order method. So it is also a single step method. So we have already discussed this. What is single step method? The slope only at the regular point. So to solve the ordinary differential equation, so we use Runge Kutta fourth order method, and it is an improvement over modified Euler's method. So and error in this method is very less comparing to previous methods like Taylor series, Picard's, Euler's and modified Euler's method. And in this method, we will find the slopes at different points, that is K1, K2, K3 and K4. At 4 points, including the starting point, are calculated, and then the weighted average of these slopes is computed. So weighted average means, so here we take the slope, coefficients of the slope. So summation of xi by summation of x. So f is the frequency. So here frequency is like 1, coefficient of k1, that is 1, and coefficient of k2 is 2, coefficient of k3 is 2, and coefficient of k4 is 1. And these are the value of k are k1, k2, k3, k4. So now, so 1 into k1, 2 into k2 and 3 into k3, and the last one is 1 into k4. Okay, so now we are taking the average of these. So 1 plus 2 plus 2 plus 1 is 6. So divided by 6. So equal weightages. We are taking equal weightages of these. So that is why we call it as weighted average of these slopes. So coefficient of k1 is 1 and coefficient of k2 is 2 and coefficient of k3 is 2, coefficient of k4 is 1. So 1 plus 2 plus 2 plus 1 is 6. So divided by 6. So weighted average of these slopes are same. Where k1 is equal to h. H is nothing but what? Step size of equal length. So h into f of x naught comma y naught. So we are taking the value of f of x naught and y naught. We are finding f of x naught and y naught. Now k2 is equal to, this is another slope, k2 is equal to h into f of x naught plus and h by 2, step size. So dividing by 2 and y naught plus k1 by 2. So next k3 is equal to another slope. We are improving the slopes. So k3 is equal to h into f of x naught plus h by 2 and y naught plus k2 by 2. So which is a step size. We are improving the step size also. And next k4 is the next slope. K4 is equal to h into f of x naught plus h comma y naught plus k3. So using this formula we can calculate. So our first approximation is y1 is equal to y naught plus k. So y naught is the previous y naught is the first approximation value, initial approximation value, and k is just now we calculated. K is equal to 1 by 6 into k1 plus 2, k2 plus 2, k3 plus k4. And x1 is the next approximation value, that is x1 is equal to x0 plus h, or h is equal to, we can write this as x1 minus x0. So step size, h is the step size. Now starting from first approximation, so we'll take the initial approximation x0 comma y0, and we proceed the next approximation. We will improve the approximation. This is x1 and y1, and next approximation is x2 and y2. We will calculate initially x0 y0, and next we will find x1 y1, and so on. So like that we can calculate the approximation. So this process is repeated until to get the solution of the required interval. So we can start the initial interval x0 y0, and we will improve the interval x1 y1, and so on. So we can proceed this process. We can repeat this process until to get the solution in the required interval. So this process is called Runge Kutta fourth order method. So example, we can see the example here. So the unique solution of the problem dy by dx is equal to minus xy with the initial condition x0 is equal to 0 and y0 is equal to 1 is y is equal to e to the power minus x square by 2. So the unique solution of the problem, the exact solution is given here. So that is, so dy by dx is equal to minus xy given differential equation. Now taking integration on both sides, so we get dy is the integration of dy is equal to, this y is sending to the left side, so integration of dy by y is equal to minus integration of dx into x into dx. So the integration of dy by y is equal to log y is equal to minus x square by 2. So y is equal to e to the power minus x square by 2 plus c. So here the initial value is x0 is equal to 0 and y is equal to 1. So now substitute here, we'll get 1 is equal to e to the power 0. So e power 0 is 1 plus c, and c1 is equal to 1 plus c, and c is equal to 0. So therefore the solution is y is equal to e to the power minus x square by 2. So this is the exact solution. Now our target is to find the approximate value of y of 0.2 with the given differential equation, that is dy by dx is equal to minus xy, and also given the initial conditions x0 is equal to 0 and y0 is equal to 1. Right, now the interval difference h is, so x0 is 0 and y0 is 1. Now our in the 0.2, so our h is 0.2, so the jump is x0 to 0.2, so the interval difference is 0.2. Or we can also calculate x1 is equal to x0 plus h. So this is x1 minus x0. We'll get the h value. Using this also we can get. So just now we have seen that xi plus 1 is equal to xi plus h. So this is the formula we can find the interval difference h. So now our target is to find the value of y of 0.2. So using one of the application of Runge Kutta method. Right, so here the given differential equation is f of x comma y is equal to dy by dx, that is, so is equal to minus xy, and y of 0, that is x0 is equal to 0, y0 is equal to 1, and h is equal to 0.2. So I'll write here h is equal to 0.2. Okay, right now we can calculate using a numerical solution of using Runge Kutta fourth order method. So here h is given 0.2 and y of 0 is equal to 1 initial condition, x0 is 0, y0 is 1, and the functional value f of x comma y is equal to minus xy. So substitute the value, finding the first slope k1. So k1 is equal to h is interval difference, that is 0.2, yes, 0.2. So h is equal to 0.2. Now 0.2 into function of f of x0 comma y0. So substitute here, the f of x0 comma y0 is minus x0 into y0. So that is, So 0 into 1, so this value becomes 0. So K1 value is 0. So similarly, we can find the value of K2, that is h into K2 is equal to h into h is 0.2 into functional value of f of x naught plus h by 2. So x naught value is 0 plus 0.2 by 2 comma y naught 1 plus k1 by 2, that is 0 by 2. So by finding this, we will get the K2 value minus 0.02. So similarly, we can calculate the value of K3 slope, another slope K3. So that is h into K3 is equal to h into h value is 0.2 into f of x naught plus h by 2. So that is 0 plus h is 0.2 by 2 comma y naught 1 plus K2 by 2. K2 value is minus 0.0198 divided by 2. So by simplifying this, so we'll get the K3 value, that is minus 0.0198. And next loop K4 is equal to h into 0.2 into f of x naught value is 0 plus h value is 0.2 and y naught value is 1 plus K3 value is minus 0.0198. So by simplifying this, we'll get K4 value here. Now we can substitute these K1, K2, K3 slopes in the given equation K. So in the formula K is equal to 1 by 6 into 1 into K1 plus 2 into K2 plus 2 into K3 plus K4. So substitute these values here in place of K1, K2, K3, K4. So we'll get the K value. Now what is the required solution? Y1 is equal to y naught plus K is our required solution, and K is the just now we've calculated K value, and this y naught is the previous value. Substitute here. So y1 is equal to, that is y of 0.2, y1 is nothing but y of 0.2 is equal to y naught plus K. So that is y naught. What is y naught? 1 minus K value is 0.0198013. So by subtracting this, we'll get 0.9801986. So this is the required solution of y of 0.2. So this is x1 and this is y1. So in this way, we can continue up to the desired accuracy solution is yet in the required interval. So in this way, we can calculate using to solve the ordinary differential equation using Runge Kutta fourth order method. So in today's session, we have discussed about Runge Kutta fourth order method. So in Runge Kutta fourth order method, so we have discussed how to solve the ordinary differential equation, and what is the difference between the above previous methods, like Taylor series method, Euler's modified Euler's, and RK method. So it has more accuracy and it takes less time, so we'll get the solution easily. So we will use this Runge Kutta fourth order method, so instead of that Euler's modified Euler's and RK method. So thank you.